Hello, I'm Ben Espy, and this is my report on Lab 5. In Lab 5, we're exploring both Faraday's law and Lenz's rule. Faraday's law shows that there is a quantitative relationship between the rate of change of a magnetic field and the magnitude of a non-Coulomb electric field. Lenz's rule shows that a non-Coulomb electric field will drive a current in a direction that generates a magnetic field to cause flux to be constant. Some of the other principles we have to use in this lab is both the magnetic field of a dipole as well as the magnetic force, which is current times the change in distance crossed with the magnetic field. And the results of our experiment was that t observed was about half a second, while calculated time was about 1.2 seconds. So some of the measurements for the tube that we were dropping our magnet through. The length of it was about 1 foot or 300 centimeters. The thickness of the foil was not very much, about 2 millimeters. The inner radius of the tube was about 1.5 centimeters, and the magnetic moment of our dipole was about 3.102. And so for our experiment, we took one long video where we dropped the magnet 5 times, and then looking in slow motion at the times that it entered the tube and exited the tube, we found the average falling time to be about half a second. And before we move on to our model, we are going to answer some of these questions. So the reason we could not use a Ferris tube is this would be physically attracted to the magnet, and so the magnet would just stick to the side of the tube instead of falling. And then because we are dropping the magnet through the tube, it generates a flux, causing the magnet to be slowed, so resisting the fall of the magnet. And so this causes the magnet to fall much slower than it would in a free space. So T is much higher than it would be if we just dropped the magnet in free space. Now for the GlowScript code, we first had to generate our magnet. And so this is the magnetic field of that dipole. As you see here, this is the code that generates the change in flux. And meanwhile, this calculates the current induced by the flux, because it's just the change in flux absolute value over R. We also see the change in the magnitude of the magnetic force. So first we had to find sine theta, which is just equal to the absolute value of the magnetic moment unit vector crossed with the magnetic field unit vector, and take the absolute value of that. And then if you multiply the current times the change in distance times the magnetic field times sine theta, that will equal the change in the absolute value of the magnetic force. And then if you integrate this, where you're just constantly updating it, as you see here, that's the same as integrating it, and so you find the total magnitude of the magnetic force in the y direction. Then you can find the force of gravity, which is just mass times the gravitational constant g in the negative y direction, and so you add these together to find the net force of this falling object. And then you can, as you go through delta t, you can update both the velocity and the position, as seen here. And so with that, you can simulate this magnet falling through the tube. And this is what it looks like in the final output. As you graph it, you see that it starts falling and it's accelerating in its fall as gravity works on it until eventually the flux begins to change, and so you see the net force even out, and then you're no longer accelerating. You have a constant velocity as you fall, until you fall out the end of the tube, in which case the magnetic flux is no longer working on it, and so it begins to accelerate again as it falls. And so again, the time calculated for this to happen is about 1.245 seconds. In conclusion, so this is actually much higher than the time that we observed ourselves. It's very likely that this is because we were not dropping the magnet perfectly vertical through the tube. And so what this does is, because it is at a slight angle, the full magnitude of the magnetic field is not in the y direction, and so the full magnetic force being resisted is not all in the y direction. And so it is not fully counteracting the force of gravity, which is why it's not going to fall as quickly. And just to answer some of the other questions, is if resistivity was as little as possible, because we know I is EMF over R. As R approaches 0, I would approach infinity, so this would cause the induced current to increase, which would then cause the magnetic force to increase, resisting it, so the magnet would fall much, much slower. And conversely, if there are holes or slots cut into the tube, the resistance would increase, and so the opposite would happen. The induced current magnetic force would increase, and so the magnet, would decrease, and the magnet would fall faster because the induced current and magnetic force resisting its fall is smaller, and so the magnet would fall faster. And thank you for your time.